Assalamu alaikum everyone, welcome to the second lecture of the antenna designing tutorial series. Throughout the series, I am Tofayel Karim, will serve as an instructor. Muhammad Ashraful Haque sir is there as a mentor, and the whole series is coordinated by Md Sabir Hossain sir. So far, we have discussed the fundamentals of antenna technology, where we shed light on antenna radiation mechanisms, antenna types, and crucial antenna parameters. In today's lecture, I am going to discuss the fundamental concepts and design procedures of a microstrip patch antenna. Before we go through the details, you may ask why we should know about microstrip patch antenna. Well, microstrip patch antennas are in business due to their outstanding properties like ease of fabrication and customization, simple and cost-friendly construction, lightweight and low volume, suitable for array antennas, mechanical robustness, and most importantly, their compatibility with MMICs. Now that we have learned why we need to know about the microstrip patch antenna, it's time to discuss its construction. There are mainly three planes in a microstrip patch antenna, namely the patch, substrate, and the ground plane. The patch acts as the radiating element of the antenna, the substrate provides mechanical strength, and the ground is responsible for reflecting the electromagnetic wave that is coming from the patch. Now, let's examine the effects of each element of the microstrip patch antenna. First of all, I will discuss how the patch affects the antenna performance. Well, a patch has an immense effect on the overall antenna performance. Its size, shape, and thickness affect the antenna's resonant frequency, bandwidth, gain, and radiation pattern. A larger patch will have a lower resonant frequency and wider bandwidth. A thicker patch will have a higher resonant frequency and narrower bandwidth. To radiate effectively, the length L of the element is usually less than lambda by 2 and greater than lambda by 3. Now, let's talk about the substrate's effect on antenna performance. The ones that are most desirable for good antenna performance are thick substrates whose dielectric constant is in the lower end of the range because they provide better efficiency, larger bandwidth, and loosely bound fields for radiation into space, but at the expense of larger element size. Thin substrates with higher dielectric constants are desirable for microwave circuitry because they require tightly bound fields to minimize undesired radiation and coupling and lead to smaller element sizes. However, because of their greater losses, they are less efficient and have relatively smaller bandwidths. The range of electrical permittivity of a substrate should be less than or equal to 12 and greater than or equal to 2.2. It's time to focus on the effects of ground on the antenna performance. The ground is the conducting plane that is opposite the patch. It reflects the electromagnetic waves from the patch, which helps to radiate them away from the antenna. A larger ground plane will improve the antenna's gain and efficiency. The ground plane should be made of a good conductor, such as copper or gold. Having known all these basic concepts, now it is convenient to look at the designing procedures of the microstrip patch antenna. To start the designing process, at the very beginning, you should select the operating frequency of your antenna, the substrate material, and the substrate material height. Once you have selected these three pieces of stuff, you are ready to go through the following equations to calculate the antenna dimensions. The equation to calculate patch width W is given below, where lambda is the wavelength of the electromagnetic wave. Epsilon r denotes the electrical permittivity of the substrate. Then, we need to calculate both effective permittivity and fringing field to determine the patch's desired length. In the effective permittivity and fringing field equation, H denotes the substrate height and W is the patch width. The input impedance ZA is calculated by the following equation. Finally, we need to calculate the depth of the feeding point using the given equation. Let's do an exercise using these equations. Here we have to design an antenna and the desired specifications are relative permittivity is 4.3, substrate height 1.6 mm and the desired frequency is 5.8 GHz. The ratio of S by WF is 1.3 where WF is 3 mm which is basically a 50 ohm transmission line. We must find the patch length L, width W and the feeding point depth Xi. So, first of all, we calculate the patch width using the first formula. To do so, we calculated the wavelength at 5.8 GHz, which is 52 mm. We have selected Fr4 as a substrate material and its permittivity is 4.3. Using wavelength and permittivity, the calculated patch width is 15.9 mm. Now the length of the patch is 11 mm, the calculated input impedance is 243 ohm and the depth of the feeding point is 2.9 mm. Let's examine the detailed effects of patch dimensions on a 2.4 GHz patch antenna. Those who are wondering, how do I get these results? Don't worry. In the next lecture, I will demonstrate how to get these results from CST MicroWave Studio software. The graph at the upper right corner shows the effect of patch width on antenna performance. Changing the patch width W shifts the antenna resonant frequency and affects impedance matching. Overall, the effect is insignificant. We see a noteworthy change on antenna performance by changing the patch length. Changing the patch length L shifts the antenna resonant frequency and affects impedance matching. Overall, the effect is very significant. It's time to focus on the effects of substrate dimensions on the antenna performance. Changing the substrate width W shows almost little to no effects on the overall antenna performance. Changing the patch length L shifts the antenna resonant frequency and affects impedance matching. Overall, the effect is very significant. To make this lecture, I used the following references. Thank you everyone for being with us. In the next video, I'm going to demonstrate how to design a 2.4 GHz patch antenna in CST MicroWave Studio. Stay tuned to enrich your knowledge on antenna designing.